Okay, so good evening everyone. I am Anjali Goel, the teaching assistant for the course Professor Vivek Dikshit uh, on the course Semiconductor Device Modeling and Simulation. So I'll be discussing a few questions. Some will be MCQs and some will be normal numerical questions. So to start with, given an energy band diagram, how do we find the electric field? So your options are it is proportional to EC, it is proportional to minus EC, it is proportional to the slope of EC, it is proportional to minus the slope of EC. So I'll wait for a couple of minutes. Okay, so it is proportional to slope of EC. So as being taught, suppose we have the band diagram. So at equilibrium, this is your EC, this is your EV when you have no gate supply. So whenever you have to find out your electric field, so basically whenever you supply, suppose I supply voltage at your drain terminal, so this gets bent downwards. So this is sort of your barrier. So you come to know that from where the field is happening. So this is from the drain potential. If you keep on increasing your gate voltage, so that will start to decrease. So this was if there's a drain. Now if you apply the gate by keeping the drain same, so if it is becoming more and more conducting. Okay, so second question, a donor atom used to dope silicon N type comes from which column of periodic table? So your options are 2, 3, 4, 5 or 6. So I hope that with N type you remember that for this you should have an electron giving. So for example, phosphorus. So I hope this is an hint. Okay, so
Fourth, fifth.
yeah, it is group 5. Okay, so what is law of mass action? So your options are N is equals to P is equals to Ni, N is equals to Nc, Np is equals to NcNb, Np is equals to Ni square, and Np is equals to 1 upon Ni square.
Both A and D.
Both A and
D.
see, the mass action law is basically this. This holds true in only in degenerate condition. Otherwise, it is Np is equals to Ni square. What is the mathematical statement of space charge neutrality?
E ray.
D or E?
E.
No, it will
Okay,
it
100.
it will be D. The number of acceptor will be equal to number of donors. And you are seeing this in the perspective that you are saying that all of this combines to 0.
Yeah,
But it is
it
never,
will be recombination.
yeah, but ideally it is the concentration of both is same. So that is space charge. Even if you have doping, so it will always maintain this space charge neutral.
Okay, we are deletion region and cannot recombine.
Yeah,
Like that.
yeah. Okay. Consider a semiconductor moderately doped N type but at moderate temperature so that the dopants are fully ionized. Where do you expect the Fermi level to be? In the lower half of band gap, near the middle, in band gap, upper half of band gap.
C, right, ma'am?
Yeah. Okay. So now we'll start with the numericals. Assume silicon at T is equals to 300 Kelvin, doped with arsenic at Nd equals to 10 raised to power 20 per centimeter cube. So you have to find out, compute the density of electrons in conduction band, compute the location of Fermi level, compute the fraction of dopants that are ionized, compute the density of holes in valence band. So I'll give you 5 to 10 minutes so that you can at least try, and then I'll discuss.
Ma'am, for ND greater than 20, for ND is equal to 10 to the power 20, we can take impurity scattering and calculate that out and right.
In which part?
I can't hear you. It's
In which part?
yeah.
A part, okay.
And then I can find the mobility. From there, I don't know that.
Okay, so see, it will just be the same. N is equals to Nd, the density of electrons. The number of that is doped.
Yeah.
So because it is very highly doped, so anything that will be, it will remain in the same power, that is 10 raised to power 20.
Okay.
So it will just be the same. The NC you can, for B part, you can take NC equals to 3.23 into 10 raised by 19 per centimeter cube, because that you might not be knowing. So yeah, you can tell me the value in terms of Fermi factor. So because you won't be having the Fermi factor calculator, so you can let me know what is in terms of F1 by 2. So you have to be EF minus EC by KBT. So this will be F1 by 2. So you have to tell me these two terms and what will they compute it to be. I'll tell you the location. Okay, first you give me the value and then I'll let you know further. Okay, so this is basically N upon NC. So you, after calculating, this will become 3.10. So when on NanoHub, there is a Fermi direct calculator. So if you use it, then the final thing you get is EF is equals to EC plus 2.184 kVt. So from this we come to know that EF is inside the conduction band. Okay.
Actually, we have a formula called N is equal to NC into e to the power EF minus EC by QT.
Yeah, it is. We can use that because that will also solve for same. So I
Yeah,
put
I
it.
got 3.10.
Yeah, yeah,
I've taken ln on both sides and I got 1.137.
yeah, yeah. Okay, okay. So have you done the C part or shall I wait?
Actually, I don't know how to do the C part.
Okay. So since we assume it that it is a metal semiconductor transition, so your Nd plus and Nd will be 1. So this is basically your fraction of dopants that are ionized. We assume that it is a transition, so the ratio is 1. So it's just the formula that we wanted to make aware. And third, you have to just use the mass action law.
Can you explain the concept behind it? C part.
See, this if EF is inside the conduction band, that means it is in its degenerate state. So since this is being in its degenerate state, so whatever we were it was asked that how much is ionized. So basically the whole thing is in degenerate, so everything is ionized. But otherwise there had to be some fraction, so we calculate by a whole derivation or using the energy band diagram. So if you want, then I can share the derivation or the whole thing with you.
Can you share the definition?
Okay, I'll mail you. You can give me your mail ID at the end of the session. So I'll mail you that thesis, the derivation.
Yeah, okay. I'll put it in the chat box.
Yeah. Okay. Okay. So in D part, you have to calculate using the mass action law. So shall I? I hope that you'll do. So I'll wait.
Yeah, I got it, man.
Okay. I'll solve the Ni square. So this will come out to be 4.68 into 10 raised by 21. So now you may solve and you'll find out that this is just equals to P. Oh no, sorry. So P will be 4.68 into 10 raised by 21 divide by, since we are converted everything into meter now, 10 raised by 18. So 4.68 into 10 raised by 3. That means N is greater than P. Okay, so in the next question, there is a band diagram question. So you can just let me know how will I draw, because as you won't be able to show me. For the sketched below, this is region is your EV. So the first thing is that you have to sketch the carrier densities Nx and Px. Your B part is potential phi x, and your C part is electric field E. So you can draw first at your notebook and then you can let me know.
From here, the number of holes will be higher, right?
Yeah,
So,
okay, so you can tell me in terms of log P of x. So how shall I draw it?
as distance increases, the number of carrier concentration actually increases, right?
Okay, so something like this.
Yeah,
Okay, and log of n of x, the opposite.
yeah.
Okay, so now the B part, electrostatic potential.
Electrostatic potential and electric field will have the same graph, but it will be in the minus direction, right? Since they both are proportional.
Okay, so this way.
Yeah,
And this will be for your electric field, somewhat more negative.
yeah.
Okay,
Okay. Yes.
okay.
It will be on the negative x. Okay, negative x.
Yeah,
It will
yeah,
be on the negative electric field, right?
yeah,
Minus
yeah,
E.
yeah, yeah, minus E. Yeah. Assume silicon at T is equals to 77K, doped with arsenic at Nd is equals to per cube. So you have to again compute the density of electrons at conduction band, location of Fermi level, and density of holes in valence band. So I'll give you 5 minutes.
Ma'am, what is the value of NC?
The value of NC, otherwise you can also calculate NC as NC at 300K into the time temperature you want to calculate, 300 3 by 2. So when you know the previous value, that is 3.23 into 10 raised to power 19. So now you can vary the temperature and you can get different values of NC. I was audible, I guess.
Yeah.
Okay.
Ma'am, the Fermi level is more intended towards EV, valence band, right? So the number of electrons will be much less
Okay.
in conduction.
Okay.
It will be a p-type semiconductor.
Okay. So what will be the value?
Um,
So you must have calculated the value of NC, EF.
I got minus 6.04 kT plus EC. I still haven't substituted.
So it is minus 7.65. I'll do the derivation. So after this, you'll get 2 into 10 raised to power 15 per centimeter cube. Okay. So going by the space charge neutrality, P minus N plus ND is equals to 0. So since it will be very less, as you rightly mentioned, so ND plus, now minus NC for me direct, EF minus EC by KBT plus the degeneracy factor, because this will not be a complete degenerate. So is equals to 0. So upon solving, if okay, I will open it. EF is equals to EC plus KBT ln N tilde 2NC 1 plus 4ND by N tilde. Okay, so where your N tilde is equals to NC by GD exponential minus EC minus ED by KBT. So when you'll replace the values, so you'll get EF is equals to EC minus 7.65 KBT, which I have mentioned. So now can you solve and give me the value of holes in the valence band? Okay, so P is equals to NB exponential EV minus EF kBT EV minus EC plus EC minus EF by kBT minus EG kBT kBT. So now using the DOS statements as well. So NV is equals to 1 by 4 the effective mass of holes and Planck's constant. So NV at 300 3 by 2, this comes out to 2.38 into 10 raised to power 18 per centimeter cube, and the band gap minus alpha t square plus t beta, these are the fitting parameters, which makes it 1.166 electron volts. So I'll tell you that alpha is 4.730 into 10 raised to power minus 4, and beta is 636. So after then you solve, so you get P is equals to 2.73 to 10 raised to power minus 55 per centimeter cube. If you have any doubt, you can ask. Okay, now similar question as the previous one, but silicon is at uh, temperature 640 Kelvin with arsenic at Nd is equals to 10 raised to power 16 per centimeter cube. So you have to again repeat. So I'll tell you the Ni concentration at 640 Kelvin. It is 10 raised to power 16 per centimeter cube. And so I hope that you can do other parameters. So I'll just give you a hint that in this you can directly use your mass action law because it is nearly intrinsic as you'll solve. So I'll give you 5 minutes and then we can discuss. Okay, so N is equals to Nd by 2 plus Nd by 2 whole square plus Ni square. So Nd is already given in the question as 10 raised to power 16. So on dividing, 5 into 10 raised to power 15 plus 5 into 10 raised to power 15 whole square plus 10 raised to power 16 whole square under root. So this gives 1.62 into 10 raised to power 16 per centimeter cube. Now you have to determine the location of Fermi level. So N is equals to Nc exponential EF minus EC by kBt. So in this, Nc is temperature dependent, as I have told you earlier. So for this, Nc becomes 1.01 into 10 raised to power 20 per centimeter cube. So EF is equals to EC minus 8.74 kBt. Now with the using the mass action law, since I told you that the holes is quite negligible, will be, and it is nearly intrinsic. So P is equals to 10 raised to power 16 whole square, because as you can see from the calculation of N also, so this comes out to be 6.2 into 10 raised to power 15 per centimeter cube. Okay, so moving on to the last question, so that I'll take it as an MCQ. Rather there'll be two. So consider a semiconductor doped N type but at temperature is equals to 0 Kelvin, where do you expect the Fermi level to be? So your options are inside the valence band, near the middle of band gap, at donor level, or C, between donor level and conduction band.
It's either B or C, right?
Sorry. No, it is D, because see, at 0 degree, you need some temperature so that your device becomes semiconductor, right?
Yeah.
So whenever you so a doping is done, so it creates a doping level, but you want it should go to the conduction band, then only you will have the current going through it, right? So that
Yeah.
is why it will be between the donor level and the conduction band. In the middle of band gap, it is not completely intrinsic, because it
It
has
can
some
also
inbuilt.
be B, right?
Yeah, so it'll be between these two, so that is option D.
No, ma'am, I'm having, it can be B, right? Ma'am?
In the middle of, if you, that depends on the band gap that you're selecting, but if we consider of a silicon at normal, so we probably take it uh, not entirely, because at 0 Kelvin we consider it to be in some sort of insulation part only, so that is why.
Ma'am, if it's the middle of the band gap means then we can take EC plus EV by 2, right?
Yeah,
EF
yeah,
is
yeah,
equal
yeah,
to.
yeah. We can take it, but the most ideal option would be between the donor level and the conduction level. We can take it, I'm not denying to it,
Okay.
but the most appropriate way of expressing anything.
Yeah.
Okay, so the last is, as the temperature increases from 0 K to a high temperature, the carrier concentration goes through three regions. So, what is the order of transition? So, I'll just, the states are basically intrinsic, extrinsic, and freeze out. So, I'll label it as A, B, and C. So, your first option is A, B, and C. Second option is B, then A, then C. Your third option is C, A, and B. And your fourth option is C, B, and A.
Fourth, right?
Yeah, this is the fourth option. Okay, so this was for today's session. So I request you to follow peer read book, because then only you'll be able to have expertise and we could discuss more in detail. So yeah, thank you.
Ma'am, can you type the book name?
Robert Pearett.
One second, ma'am. I
Yeah,
can
yeah,
take.
no issues. The name of the book is Advanced Semiconductor Fundamentals by Robert Pearett. It has given, it is a difficult book, but it has given every concept in very detail, and you can find each with the help of a band diagram. If you want to go for a basic book that basically I follow, apart from what Sir is teaching in the NEPTEL, so that is Neiman, the book
No,
by
that also is Streetman and the Bench.
Yeah, Streetman also, but we basically follow in my college when I was doing the coursework, and since my thesis is also in the same device modeling, so basically we follow these two books, and it covers all the topics that Sir is teaching. In addition to what, because I just gone through the book that Sir Vivek sir has referred while I'm going through his teaching. Otherwise, the as far as I've learned from my professor, so we have followed these two books.
Yeah.
Okay, thank you.
Yes, thank you.